Wonderful. Well, thank you very much, Christoph, and thanks everybody for sticking around toward the end of the afternoon and evening here. Um, SunRay Scientific has presented different topics in the past about our ZTACH technology. Today, we're going to be talking about the UV curable version of this. This is a big innovation for the technology. It's a big innovation for our customers. And we're going to talk a little bit about some of the data and some of the progress we've made in the development of this. And I'll give you a little background on the technology for those who have not been exposed to it before. So let me dig right into it. Just to give you a little background on who we are, we're an innovative materials developer and supplier. Similar to what was explained in the VTT slides earlier that they gave, we do things a little differently because ZTACH is such a unique technology. We've put in the capabilities. We've just moved into a new 11,000 square foot facility a few miles from our previous location. And we have installed a full SMT line with all the automated placement equipment, printing and deposition equipment that can help people that we're working with, both at the OEM level and contract manufacturers, to characterize the performance of our technologies in their parts and then build out a fully scalable manufacturing process on our line that we can then transfer to theirs. So we can bring all these different resources to bear on the left. We do a lot of prototype development work for OEMs who want to integrate our technology into their process, and this is how we do so. A little background on the technology in general. So ZTACH is an anisotropic conductive epoxy, but it is not a film-based material, and it has a lot of unique attributes that are unlike anything else that currently are available. Many of these include the fact that not only are we not patterning the material because of its anisotropic nature, but it does not require any exceptionally high amounts of heat or any pressure to functionalize. So unlike ACF, ACA, and ACPs, where you use a thermode to provide both the heat and pressure to functionalize that anisotropic property, we're doing it by way of a magnetic carrier pallet that carries the printed electronic materials through the curing process after it's gone through SMT and had the components placed on it, which provides a magnetic field that creates column alignment using our ferromagnetic particles. And that gives us very direct line of contact, intimate interconnection electrically, and it gives us very good isolation between the columns. In the case of our thermally cured material, that's a two-part polymer epoxy that gives us very good insulation between these columns and very low resistance between typically 7 and 20 milliohm centimeter. So it's going to be more conductive than typical ECA, ACF, or ACA, not as conductive as pure metallic solder, but lower than most of the other applied materials that would typically be used. And the other unique property here is because we are just underfilling the entire component and then creating that anisotropic property during the cure process, we have a lot lower volume or solids of these ferromagnetic particles, which are encapsulated either in silver or gold. And because it's much lower in solids, the majority of this 100% solids composition is the epoxy or the adhesive, which gives it exceptionally high bond strength, much higher bond and shear strength than you would get with typical conductive adhesives. Often which results in the ability to not have to have any kind of encapsulation to keep the component in place afterwards. So we're not using pressure. We can process the thermally cured version down to 80 degrees C and up to 160 degrees C with different types of application requirements where that's needed. Superior adhesion, exceptional bond strength, RF performance up to 90 gigahertz. It's very durable bond, so it enables high flexibility, high stretchable, high bend, and qualifications with different contract manufacturing partners. We can pass quarter-inch mandrel bend of an LED component of an 0402 size without any encapsulation, and we're achieving over 98% yield with that. So it's excellent in attaching to curved surfaces. It also doesn't require coplanarity between the substrate and the component. So when you have dissimilar surfaces, we can still make that interconnection because we're using the magnetic field to get those particles to grow into these uniform columns that you see on the bottom right. Additionally, we can manage very fine pitch. Right now with our standard fine formulation and in high density, so we've placed on a full-size printed electronic